Hi! UMD Loop proudly presents Palamedes, our third-generation rover built by a team of 54 students representing the University of Maryland College Park.
To traverse a variety of difficult terrain types, our team has developed new 3D printed TPU wheels. A new mounting bracket improves mechanical efficiency, simultaneously increasing top speed and traversable obstacle height. Our brand new steering mechanism uses two Maxon motors to optimize weight and performance. Additionally, our differential rocker suspension system improves maneuverability and stability while protecting against strong impact forces. As you can see, Palamedes navigates smoothly across harsh terrain types such as gravel, rocks, mud, and sand.
Our rover's electrical system aims to be as modular as possible, utilizing standardized connection points and controller area network to distribute power and communications. Our power distribution module manages a 24-volt and 15-volt battery to isolate actuation from computing and communications respectively. An e-stop system uses relays and a custom voltage monitoring board to allow for safe shutdown of the rover during emergencies. A propulsion module on each side distributes power and CAN communications to two brushless DC motors. An O-Drive Micro powers our steering motor and allows for CAN-compatible actuation commands. Additionally, this module is being used to test custom axial flux BLDC motors in mid-stage development. From the power distribution module, a single 9W4 connector provides power and CAN communications to both our ARM and Science modules.
This year's 7 degree of freedom mechanical arm system is designed with a new belt-driven elbow to increase stability and carrying capacity. Our team also uses different specialized wrist and gripper combinations for each mission. Our new differential 3 degree of freedom wrist is used in the delivery mission alongside a parallel linkage gripper, while our 2 degree of freedom wrist and lead screw gripper is used in the equipment servicing mission, interacting with buttons, flipping switches, connecting a hose, placing a test tube in a slot, and recovering data from a USB-C connection. Our autonomous typing stack blends precise camera placements with custom computer vision algorithms to track positions between relative frames, allowing for pinpoint autonomous typing accuracy. Additionally, our arm is fully capable of lifting up to 5 kilograms of weight at full extension in every one of its configurations.
Our Science module's Life Detection Suite features a custom Raman spectrometer and steady-state fluorometer to search for biosignatures. Our Raman spectrometer focuses a laser into our sample, emitting a Raman signal, which is reflected into our system and processed by our CCD sensor to generate a spectrum. Our custom fluorometer filters an LED to excite chlorophyll, where fluorescent light is detected by a photodiode. Both life detection instruments are contained in our modular science box, which also houses our sample collection mechanisms. The two soil scoop modules each collect a 5 to 10 gram sample that are connected to a series of sample transportation tubes. Distilled water is pumped into the soil scoop where it is mixed with the sample. The slurry is then pumped back out of the scoop and is filtered for analysis. Finally, our subsurface sampler collects and caches a sample from below 10 centimeters. The cache is then sealed with magnets and can be easily detached for submission to the judges. Our discussion with the judges will analyze our collected data and the significance of our experiments.
Our software stack, running on a Jetson Orin NX, implements the ROS2 control, MoveIt2, and Nav2 libraries under the ROS2 Humble ecosystem. We use an open-source hardware interface for the O-Drive motor controllers. We also implement a custom CAN protocol for our team sensor and actuator PCBs, and custom hardware interfaces for the proprietary RMD, SMC, and Talon motor controllers. For high-level control, we've implemented a joint-by-joint controller for the ARM, single Ackerman steering for drive, and a custom manual controller for Science.
Our base station, featuring 5 vertically mounted monitors, each correspond to a specific role during command and control. All the while, our base station can be set up and packed up in less than 10 minutes.
Our drone was designed for 20 minutes of theoretical flight time and a maximum speed of 52 miles per hour. By using the drone as a radio relay, we can extend our rover's communication range far beyond direct line of sight.
For autonomous navigation this year, we utilized the Nav2 framework, combining a Z2i and RTK GPS for accurate perception and global positioning. The Z2i provides depth, visual odometry, and object detection, allowing the rover to understand its surroundings in real time. Utilizing USGS LiDAR data of the MDRS site, a global cost map is built, which the rover navigates using an A*-based algorithm. With the path planned, the rover executes it autonomously, with factor graph-based localization for state estimation and a YOLO V8 model for real-time object detection. Obstacle avoidance is implemented using the Z2i's depth perception abilities. A custom search algorithm is implemented using goal poses generated by an Archimedean spiral from the designated GNSS coordinate. And a Ruko tag detection algorithm allows the rover to reliably stop within 2 meters of the post.
Rigorous testing, iterative design, and operational practice have prepared both our team and our rover for competition. We are UMD Loop, and we will see you in Utah.